everyone. Thanks for coming back after lunch. I know that that's hard, so I appreciate it. And thanks for the introduction. And hello, DevFest. My name is Katie Hockman, and I'm working over at Datadog on their tracing tools in Go. Before that, I was at Google for several years. I worked on the Go language while I was there on a few engineering efforts. One of them was the Go module mirror and checksum database, which provides safe, secure, reliable Go source code to Go developers. And then I worked on security and cryptography for the language. And what I was most excited about, which I get to talk to you about today, is fuzzing in Go. So I was the engineering lead and design for that feature. And there's so many neat things to do and learn with fuzzing. So let's jump right in. So when you're looking at the title of this talk, the first question you might be asking is, what does fuzzy mean? Like, what does it mean for a test to be fuzzy? So the first thing I did, as many of you might do, is go to Google and type in the word fuzzy and see what comes up. So the first definition is something that's having a frizzy, fluffy, or frayed texture or appearance. So clearly, this is a fuzz test, obviously. OK, well, so these are really cute. But unfortunately, this isn't quite the kind of fuzzy that I'm looking for here. OK, so not definition number one. What about the second one? Difficult to perceive clearly or understand and explain precisely. Indistinct or vague. I think this word indistinct is the one we should be paying attention to. If your testing is indistinct, then it isn't sharply defined. And that's the main difference between other kinds of tests, like unit tests, and fuzzing. When you write a unit test, you give your system a carefully crafted input, and then you verify the output. The expectations are deterministic. They're sharply defined. A fuzz test, however, is going to work around the edges that you're already testing, blurring the precise lines through your system that you already know about. It's exploring code paths that are atypical and unexpected, which may turn up equally unexpected results. Fuzzing isn't going to replace your unit tests, but it can find some very neat bugs that your unit tests might have missed. So before we jump into fuzz tests, I know some of you may never have even used Go before. So I want to make sure you understand how unit tests work in Go first before we jump into fuzz testing, because that's an important concept to have as a foundation. So this is how you could write a test for the filepath.base function. You can call this function several times for different inputs and check the output. The filepath.base function, what it's doing is you give it a path, like a/b/c, and it gets you the base of that file path. So in this example, if you give it abc, it'll give you abc. If you give it a/b/c, it'll give you c. If it's different from what you expect, you fail the test. A more typical way of doing this, however, in Go is to write what's called a table-driven test, or table tests for short. It allows you to define all of your inputs and expected outputs right at the beginning of your test and avoid code duplication. So inside of that function, you're running the same code every time over different inputs and checking the output in the same way, but checking it for different inputs in unique ways. So these tests have three main parts. Part one, define your test cases, define your inputs and your expected outputs. So in this example, I have a path, I have a want. So the path is the input, the want is what I expect the output to look like. So if I pass a/b/c, then that last one there, I expect to have c. Second, you're going to loop over your test cases and execute a t.run function. For the purposes of this talk, it's not super important that you know what t.run is doing, but at a very high level, it's basically creating a subtest for each test case inside of a separate Go routine. And then finally, you're going to define what's going to be run for each test case over each input inside of your t.run function. So it's actually accepting a function that you write. In this case, we're going to call filepath.base for each input. We're going to check if what we got is the same as what we wanted. And if it's not, we're going to return an error. We'll fail the subtest. The running tests in Go is going to be using the Go tool, the Go command. The Go command, if you've ever used Go before, it's basically the backbone of all Go tooling. It's what you use to build your code, run your code, test your code. The default mode of Go test is to run all of the tests in that directory. You can also run Go test with a package name, and that will run all of the tests inside of that package. There's a lot of different ways you can customize this tool. These are some of the more popular ones. For example, Go test-run that matches the regular expression that you provide it, and will only run those tests in that run. So in short, to summarize, with unit testing, you provide the input, you verify the output. Fuzz testing, however, is a little bit different. You are not defining the inputs anymore. The fuzzing engine is. And then you are going to verify that the output looks reasonable to you and looks like something that would be potentially correct. So let's take a moment to walk through a very high-level overview of what's going on when you're writing and running fuzz tests. First, you provide some starting values to the fuzzer. This is going to be especially helpful if you're trying to fuzz more complex data, like HTML or JSON or some very structured input in some specific way. Fortunately, if you've written unit tests or you have test cases that you've already been using, you should hopefully be able to just use those again. So you shouldn't have to do any extra work here, in theory. This is also an optional step in Go, but it does make fuzzing more effective sooner. After that, fuzzing is going to start. The fuzzing engine is going to look at the starting values. It's going to perform mutations on those values, and it's going to start testing your code. The Go fuzzer can run like hundreds of thousands of inputs a second. It's a lot of inputs that it's running against your code. And it can actually find bugs based on how you're writing it. And this is where the magic is going to happen. And I'll show that in my demo later. And finally, if a bug is found during fuzzing, hopefully the system should tell you about it, right? That's what you're doing, you're bug hunting. So let's jump right into a bit of code so you can learn how to do one of those yourself in Go. First, we're going to define a fuzz test. This is the overarching function of the test, much like a unit test or a benchmark would be. This can live right next to your other unit tests in that _test.go file. You'll see that in my demo, too. In the same way that a unit test accepts a testing.t and a benchmark accepts a testing.b, a fuzz test accepts a testing.f. This testing.f type is new for Go 1.18, and it provides the functions you need to write and run your fuzz test. It works a lot like testing.t does, just with a couple of different or additional functions. Those two additional functions are f.add and f.fuzz. f.add is going to be used to provide those starting values I was speaking about before. And f.add is going to be what you provide a function to, which is going to be what's actually running when you're doing your fuzzing. OK, so now that we have our fuzz test defined, the first thing we're going to do inside of this, again, this is optional. I'm going to do it in this example, though, is we're going to call f.add. These starting values are going to be kept in something called a seed corpus, which I'm going to talk about in just a moment. So don't worry if you don't know that term yet. Every call to f.add is going to correspond to one entry in a seed corpus. So you can call this function tons of times. If you call it 10 times, you're going to have 10 things in your seed corpus. You can also do any preparation for your fuzz target here, much like you would do for a unit test before you loop over the test cases and run your subtests. You can do any pre-work, that one-time work that you do that has shared values across your testing. And finally, the fun part. You define your fuzz target using f.fuzz. f.fuzz is going to take a function whose first parameter is a testing.t, kind of like a subtest in and of itself. And then the remaining parameters are going to be the fuzzing arguments, which inform what kinds of data the fuzzing engine is going to generate and give to your test. The fuzz target will then be called over and over and over again, millions and millions and millions of times as fuzzing goes. And that's it. You can write a very simple yet very effective fuzz test in a couple lines, 5 lines of code-ish. So it's hopefully pretty simple to write one for your code if you would like to. OK, so the word that I mentioned before was seed corpus, and a term you're often going to hear around the fuzzing space is the word corpus. So let's just take a moment to explore this term so you know what's happening when you're running it. The corpus is a collection of inputs that guide fuzzing. So simple in that sense. For the Go fuzzer, a corpus is made up of 2 pieces, the seed corpus and the generated corpus. The seed corpus is a user-provided data set which can be used to guide the fuzzing engine. It's sourced from 2 places, f.add calls, and the files in the testdata/fuzz directory within the package that's named after the fuzz test. It's a bit of a mouthful. I'm going to show you that during the demo, too, so you can understand it a little bit better. The seed corpus also serves an additional purpose in Go, running with Go test by default, even when fuzzing isn't running. That can actually serve as a regression test of sorts, and I'll show that in the demo as well. The generated corpus, on the other hand, is machine-generated rather than user-defined. And it's maintained entirely by the fuzzing engine. You should hopefully never have to touch this, never have to look at it, but it is nice to know that it's there. If fuzzing stops, let's say it finds an error, or maybe you just decided to stop it after it's run for an hour, this machine-generated data set can help it pick up where it left off and keep track of the things that it finds interesting as it runs. So here's a small example to illustrate how the fuzzing engine uses these two elements of the corpus while it's running. So the first thing it's going to do is it's going to gather all of the inputs from both the seed corpus and the generated corpus. It's going to feed each of those inputs into the fuzz test to make sure there are no crashes at the start and that we're starting in a good, clean state. And then the fuzzing engine is going to start mutating all of those entries in the corpus and feeding them to your fuzz test. If it finds something interesting, it's going to add that entry to the generated corpus and keep fuzzing, so it won't stop. However, if it finds a crash, meaning a panic in your code or something that caused an error, for example, it will stop, and it will add that entry to your seed corpus as a crash. So let's take a break here and jump into the fun part, which is the demo, so you can see how it's working in action. OK, so I have this function. This is in the strings package of the standard library. It's called, I actually don't want this one. I want index any. So I'm going to be running over index any. So let me just read the Go documentation for this one. It says it returns the index of the first instance of any Unicode code point from chars in S, or -1 if no Unicode code point from chars is present in S. So it's actually a little bit easier to understand, I think, with examples. So these are some of the tests. It's a table test like I was showing before. So you can have something like AAA, and you provide it A, and it will return 0. If you give it an empty string and then ABC, it will return -1. ABC, XYZ, -1. This one's more interesting, ABC. And XCZ, this C here, shows up in this 0, 1, 2 index of the entry, so it'll return 2. So when I look at this code, there's kind of a lot going on here for something that seems pretty simple, right? There's some special checks over the length, and it's doing some interesting things here if the length is too big or too small, and it's doing a loop. There's a lot going on. So I've taken it upon myself to write my own version of this that I hope will work. So this is my index any, and it's as small as I could feasibly make it for my own testing. So all I have is a loop over the string, and then this is going to be each character in the string. And I'm just checking, does any of the basically strings that contains of chars, does it have anything in this character here? So strings.contains chars, if C shows up in chars, it will return true. And at that point, I'll return the index. And if it doesn't ever show up, it's -1. So here's my test. I wrote a unit test. It's pretty simple. It's got lots of test cases. I'm running with t.run, like I was showing before, giving it a helpful name so I can debug it. And I'm just checking, OK, this is what I got, is the output from my index any. If my got is not the same as my want, I return an error. So let's go ahead and run that so you can see it. So I will do go test, and it passes. OK, cool. So I should just stop here, right? I've done a test. There's a lot of test cases there. I think there's like 11. That's a lot. I could say, OK, I've done 11 cases. I've got special characters in here. I've got different ways of encoding the string. I've got a lot of stuff here. So I've tested my code, and I'm done, right? You could do that. I'm going to take it one step further, and I'm going to write a fuzz test instead. So let's start that based on the example I was showing before. So fuzz index any. It takes a testing.f. And then I want to figure out what starting values I want to do. In this case, I could do none, because it's a fairly simple code. There's no special structure. But just for the sake of this, I'm going to use the test cases that were in my unit test. These I just made for myself to make it easier. Basically, all it is the same inputs that I had up here, just without the output, because I don't need to worry about the output in this case. OK, so I have all of my tests. So let's go ahead and loop over those and add them to my seed corpus. So I'll do a range over my tests, and I will add each of those to my seed corpus. Cool. So I've done f.add and given it 2 strings, which means that my fuzz target now also has to use 2 strings. I can't do different things there. It has to be consistent across the board. So let's go ahead and define our fuzz target. So it takes a function whose first argument is a testing.t. And like I said, it takes 2 strings, so that's what I'm going to do. I'm going to tell it, hey, give me 2 strings. And now I get to figure out what I want to test. So this is the part that's going to be probably the most tricky for you when you're running fuzzing. What do I put in my fuzz target? What do I fuzz? How do I fuzz it? So I could, in the very simplest way, just do my index any s chars. That may be enough for you. All that's going to do is make sure that if there's some panic, like for example, I'm accessing an index in an array or slice that isn't there and it crashes my program, it will report that. And there are a lot of fuzz tests out there that only look like this and do find panics and security vulnerabilities and are worth doing. So this on its own does have value. But I can actually take it a step further in this example. I have this function, right? I said I have index any from the strings package inside the standard library. And I am trying to write a simpler version or a faster version or whatever you decide to do. And I want to make sure it has the same behavior. So if I already have a reference implementation that I know it must match, I can use something called differential fuzzing. So it's kind of a big word, but it's not that complicated. Really, all you're doing is you're fuzzing the difference between 2 inputs, basically, between 2 functions. So that's what I can do here. So I'm going to, instead of doing that, I'm going to take it one step further. I'm going to define my got and my want. I'm going to say I got this from my function, and I want this. And if they're not the same, then I have a problem, right? I want the output of my function to be the same as the output of the one in the standard library. So at this point, let's just write a helpful error message if I hit this situation. So I'll do t.error, and let's say I'll do 2 strings here. So that's my input and my output, and then I'll say my index any yielded this integer, and the strings index any function yielded this integer. So got, want, schars, got, want. So this is just a way of helpfully formatting strings in Go. So this is going to have s, this should have chars, my index any's output, and the strings index any function. So let me just start by testing it. If I just run go test, still passes, right? OK, so we're good. And let me actually show you if I do go test -v, that's in verbose mode. So you can actually see if I do that. You don't want my debug console, you want my terminal. We're not debugging that way. So you can actually see all of the tests that are running. So you can see that it ran each of my subtests for my unit test. But notice it says seed 0, seed 1, seed 2, all the way up to seed 10. That's because it was running all of my seed corpus values by default with go test as well. OK, so I wrote my fuzz test. I wrote my unit test. So let's do the fun part and actually run fuzzing. And let's see how long it takes for it to find a bug, if there is one. Maybe I wrote perfect code. I don't know. We all have good hopes about our code, right? So I'll say fuzz index any, and we'll see how long it takes for it to find a bug. OK, so I didn't get to finish my sentence before it found a bug. So I'd say that's pretty fast. So let's look at this output and see what's actually happening here. So it said it was gathering baseline coverage. All that means is it was running, like I said before, it took all the values of my corpus, and it ran them to make sure there weren't any crashes to start with. So that's what that is. And then now fuzzing with 10 workers. So now it's basically just going to use all the resources in my machine that I will give it to run it. So if you're running fuzzing on your machine, your fan is going to go wild. It's going to be very hot. So you can always reduce the number of workers that are running. In this case, I just ran all of them. And then it says minimizing 70-byte failing input file. This is a very important line. What is that saying? It's saying it found a failure that was 70 bytes long, and then it minimized it. So it could have just given me a 70-byte failure, and then I could have tried to debug that. But that's a lot to do. So what it did is it tried to minimize it to be as small as possible so that when I look at it, I could debug it easier and faster. So here is actually the error message that came from my minimized input. It said that these 2 strings, given that way, my index any said -1, but the strings index any said 0. That's kind of weird, right? Huh. And then it said it wrote my failing input to this file. So let's go check out that file and see what's going on. So this is my corpus value. Remember how I said that the seed corpus is made up of f.add calls and the ones inside of your test data fuzz directory? So this fuzz index any directory inside of test data/fuzz, all of this was generated automatically by the fuzzing engine when it found a crash. And it just wrote this file for me. And you can see that it has the same inputs here that were showing up in my error message. I can also rerun it. It says to rerun it, I can use go test. So that has that -run I was showing before. And it's just going to run that again. So I can see I have a failure. So there's a problem here. And I need to debug it. So for those of you who have used Go before, you may know by looking at this what's going on. So I'm just going to give you a moment to just look at this code and see what you think. Don't shout it out, but just think about it. Do you see the issue? It's a little bit insidious. It's a hard one to find. So here's what's actually happening. If I change my code to contains rune instead of contains, and I give it the rune, which is the character here, it's ranging over runes with this C value here, then at that point, I'm going to have a passing test. So this is a weird one. I definitely recommend you reading about strings and byte slices and runes and bytes. There's amazing blog posts about that and documentation about that. So definitely take some time to read it. But what's actually happening is that this index any code is going over the runes. When my code was running, it was going over the bytes. And in Go, those are different things. You can have a rune that has multiple bytes. And what's happening is it's going in this index rune function, and it's seeing my failure here. And it's seeing this, even though they look different here. These are both technically the error rune. So if I actually change my test here, you can see it a little bit easier. It'll show up with a little question mark, or at least it should. So let me just do my go test again. Well, I fixed the code, so now it won't, but I'll break it again so you can see it. All right, so let's see that there. See how it's a little question mark? That's because they're both the error rune. And technically, those are both the same. So technically, that's supposed to be 0, and I'm supposed to have, and I had -1 because I said they were different. Now, whether this is a bug in my code or a bug in the standard library is kind of up for debate still. I need to file an issue and discuss it a little bit, because it's kind of strange, right? But let's go ahead and refix our issue here and make sure it passes. So I'm going to run go test again, and it passes. Yay. So let's just do go test again with the verbose mode on, and you can see that it ran, again, all of my unit tests, and it has this new one here. That's because it ran this as a regression test. So now you have a fuzz test, you have a regression test built into it, and you have your code fix. And you can just check all of that into one basically commit in Git, for example. So you can see that I have those 3 changes. I would commit all of them into one and say, here's my fuzz test, here's my regression test, and here's my fix. And that is the demo. OK, so now that we've seen our demo, you might be wondering, how is this magic happening? How is this working? So let's just take a moment to dive under the hood a bit and actually see how the fuzzing engine is working in practice. So as we've discussed, the fuzzing engine is what's responsible for generating the inputs being tested. And this isn't something it can just do however it wants to. It needs to do this effectively and quickly. Getting this right is going to be essential in having an effective fuzzing system. So one approach the fuzzing engine could, in theory, take is just complete randomization. There is a theory. It's called the infinite monkey theorem. And it basically says that a monkey hitting a keyboard at random would eventually type up the entirety of Shakespeare, given an infinite amount of time to do so. Well, we don't have an infinity amount of time to do this. We don't have an infinite amount of time. We want to find bugs a little bit faster than that. So let's just do a little bit better if we can. So let's dive into 3 issues with this naive fuzzing approach. 1, it's generating completely unrelated inputs. 2, it's ignoring the outcome of previous runs. And 3, it's structure agnostic. It's not paying attention to what kind of data it's useful for it to generate. So let's start with the first one, unrelated inputs. Why would this be an issue? If the fuzzing engine is generating completely random inputs, you may end up with a sequence of bytes that look something like this. There's no discernible pattern, and they're very random, right? This may actually find bugs in some systems, but it's not going to be very effective for most of them. Let's say you're actually fuzzing an HTML parser. You could provide a single input that looks something like this to the fuzzing engine. At that point, the fuzzing engine can mutate this input rather than starting something over and building something completely random. And maybe this is what it does the second time, third time, fourth time, fifth time. At this point, the fuzzing engine is mutating it with some level of randomness, producing values to test that are a lot more likely to expose bugs and test your system in interesting ways. OK, another reason the naive fuzzer is going to be ineffective is it's completely ignoring the outcome of the previous runs. So let's go back to our previous example again. If you're testing an HTML parser, there's a good chance that this input right here is pretty interesting to you. You provided an HTML tag as the initial input, but it generated an anchor tag. That's likely to hit a new code path in your parser that your previous test case didn't hit. So the fuzzing engine should take note of this and pay attention. It should save this input to the generated corpus as an interesting input, and not just apply random mutations to the initial input that you provided, but it should also mutate this new input it found in hopes of expanding coverage. You can almost imagine your code as a tree with different input branches off into different parts of your code and produce different outputs in the form of leaves. The fuzzing engine's goal should be to try to reach as many leaves as possible, or as many unique paths through your system as possible, with coverage as a goal. And last but not least, let's talk about the structure of the inputs being tested and why the fuzzing engine should care about this and be paying attention. Let's say you have a function, foo, which takes an int, a string, and a byte, and you want to fuzz it. If the fuzzing engine is only generating byte slices, just raw bytes, you could theoretically work with this. There are a lot of fuzzing tools that work this way, and this is basically what you have to do. You basically break it up into sections, and then you're saying, OK, this first section I'm going to treat as my string, and this section I'm going to treat as my integer, and so on. But not only is this an eyesore, it's going to waste a lot of time generating bytes that can never actually be fed into your function. One of these two returns is likely to get hit fairly often, which is going to waste our computing time, right? The fuzzing engine doesn't realize, it doesn't know. You haven't told it what it needs to do, so it's going to generate something completely random. It doesn't know how many bytes to do. It doesn't know how they should be structured, what they should look like. But if the fuzzing engine can know the structure of your function from the beginning, it can be a lot smarter about what it's giving you to test with. Plus, code like this is going to be a lot easier to understand and read and isn't going to be as error-prone. You don't want a bug in your test. That would be really frustrating. OK, so there are several issues with this naive fuzzer that generates inputs at random. So let's make our fuzzing engine even better. Go's fuzzing engine is mutation-based, so rather than generating random inputs from scratch, it's mutating existing valid inputs in different ways. It's coverage-guided, so it's paying attention to which parts of the system are being hit for each input, learning as it goes and attempting to expand code coverage as it runs. And finally, it's structure-aware, using the format of the inputs to our advantage, so the fuzzing engine avoids running through inputs that will never be valid or interesting to us. So now that you've seen it in action, you understand a bit of how it works and why it works that way, you're hopefully having this thought in your head. I want to use this. How can I use it for my project? You may have watched the demo, though, and said, well, that's not really how I can do it. Maybe I'm not accepting 2 strings and producing an integer, or maybe I don't have a working solution of an API that I can apply differential fuzzing to. Does that just mean you're out of luck and you can't do it? Of course not. There's so many different applications of fuzzing and different ways that you can use it to your advantage. So I want to spend the remainder of my time talking through some of the common questions that I've seen and some of the common scenarios and setups I've seen, so you feel fully prepared to write fuzz tests yourself for your code after this talk. So let's start with a common question. What if I don't have a working reference implementation? There are going to be a lot of times when you do. For example, you're refactoring your code. Maybe you added a feature flag. For example, you want to make sure that it's the same as it was before when the feature flag is off. Maybe you're making a performance optimization. You want to make sure the behavior hasn't changed. Those are all situations where you could use differential fuzzing. But maybe that's not what your code is like. Maybe you have a function that's been around for a while, and you only can use that, and you want to fuzz it. So you want to be able to verify the correctness of it against a canonical implementation, but you don't have one. That's OK. Let's say you want to fuzz the file path.base function, which returns the last element within the provided path string. The first step to fuzzing, just like any kind of fuzzing, it's not unique in this way, is to understand how your code is supposed to behave, right? And make sure that's happening. So if we're writing a unit test, you could provide an input and check for the expected output. We pass ABC, we get ABC. We pass ABC/DEF, what do we get? DEF. However, we can't feasibly check every single specific input's expected output when there's millions of things being generated from the fuzzing engine, nor should we. That's not really what it's for. What we can do instead is consider the properties of our function that we want to check. In the case of file path.base, one property we could be checking is that the output is a suffix of the input, right, after trimming off any of those trailing path separators. So here's a simple yet effective way of fuzzing that file path.base function with that property. First, we'll just trim off any trailing path separators at the end of the path so we can do our checks. If the path is 0 at that point, the length is 0, we're just going to skip it. And then we do our function. We call it with the path. We get the base. And if the path has a suffix of the base, if the base is a suffix of the path, essentially, then our property has been met. If not, we have a bug, and we should report that error. But do want to note a very important caveat to the example I provided. Remember, fuzzing should not be replacing unit tests. They supplement them. But fuzzing can definitely find bugs that unit tests miss, so they have value. But there are going to be situations where the properties you're verifying in your fuzz test don't completely verify correctness. So take our file path.base example again. If we're trimming off those trailing separators and we're ensuring that the output is a suffix of the path, then in all of these examples, the output is correct. It meets the property, and it's correct. But what about this one? By that logic, our property-based checking and fuzzing should also think that this is right. B/x is a suffix of A/B/x, so we're good, right? Well, no. We know that the base is x. So there's nothing wrong with fuzzing our code in the way we described, but it shouldn't give you a false sense of security such that you don't write unit tests as well. So just remember, fuzzing should supplement unit tests, not replace them. Another question you might be asking yourself, what if I'm fuzzing complex types? In the demo, I was using 2 strings and taking an integer, but what if you need something else for your fuzz test? As of the latest release in Go 1.19, Go only supports fuzzing a set of primitive types listed on the slide. That's strings, bytes, slices, integers, floats, and so on. But don't be discouraged if the types you need aren't on this list. We can still work this way. This is probably what you want your fuzz test to look like. So it just has a struct as the input, and then you can just use it. Unfortunately, that's not supported today. Hopefully, it will be in the future. There are features in the works and features on the GitHub issue tracker for the Go language. But this isn't possible today. But have no fear. You can still do this. With just a few more lines of code, we can still fuzz the method you were wanting to fuzz. Instead of passing a struct as a fuzzing argument, you should just instead pass the data you need to construct your struct and then use it. So in this case, I have a string and an integer, and then I'm just using that to create that person object that I need, and then I can use it. So there's not that much extra code that you can do. All right, what if you're fuzzing a parser? Lots of us have parsers in different kinds of ways. Well, there's some neat tricks for parsers that I really like. Let me show you one of them. So let's say your parser takes a byte slice and returns a struct foo. First thing you're going to do is you're going to unmarshal those bytes into that struct. If there's an error, that's probably OK. I mean, there are probably situations where the bytes coming in aren't valid. So we'll just skip in that case. If the data isn't valid, ignore it, move on. OK, so if we're at this line in the code, we know that it successfully unmarshaled that data into foo. So let's remarshal it again. We'll take our struct. We'll put it into, we'll take our byte slice, and we'll put it into a struct. And then let's marshal it back into a byte slice again. So we've just done a full loop. So those bytes should be the same. If they're not, then something happened in our unmarshal function or our marshal function. Let's take it one step further. Let's unmarshal those bytes again. So we've taken the same bytes and we've unmarshaled it twice. At that point, if it succeeded the first time and failed the second time, that's probably not great, right? So we should fail if it has an error, and we should fail if those two structs aren't the same. OK, let's talk through one more. To make the fuzzing engine more effective, remember how I said you want to be providing those starting values? What if your starting values are very, very big? What if there's like huge binary files, like they're a couple megs, and you don't want to put that in that underscore test.go file? It's going to pollute the file. There are ways to get around this, and here are two good options. Option number one, let's make a directory with several files in it, where each file is going to correspond to this large set of bytes that we want. So it's going to correspond to a single seed corpus value. So it's going to be kept inside of the separate test data directory, much like you would for a unit or an integration test. We'll read from the directory. We'll get all the files out of it. And this is all in that pre-work section of our fuzz test. We'll range over the files. We'll read the contents of it. We'll get some bytes back. And we'll call f.add. At that point, we have what we need. We've added all of those data points to our seed corpus. And now it's up to you to fuzz this however you want to. You can check properties, check errors, perform operations, whatever you want to do. That's up to you. Or you can just call a function, make sure it never panics. Like I said, that's a completely valid way of doing that. That's your choice. Option number two allows you to eliminate that boilerplate that I was talking about before and utilize the test data directory for that fuzz test. I want to pull this slide up again to refresh our memory. Remember how I said the seed corpus is made up of two components, f.add calls and the files inside of that test data fuzz, whatever it's called, directory. So we're going to use that instead. There's actually a tool out there inside of the xtools repository called file2fuzz, and it converts binary files, such as those used by GoFuzz, which is a separate tool that's in the community, to the Go fuzzing format that is used. So basically, you can have a bunch of these binary files. You can feed them into this tool, and it will generate the corpus files that we actually need that are structured and formatted in the way that we want and coded in the way that the fuzzing engine needs. And we'll just pop all of those into that fuzz foo or fuzz index any or whatever that's called directory, and then we're good. And this is going to recognize these seed corpus entries in the exact same way as if you had done it manually with f.add. There are a lot of what-if questions there. There are so many scenarios that you can run into as you explore fuzzing. And you may have questions. You may have ideas for how to make this better. So I highly encourage anyone who's interested in fuzzing Go code to join the fuzzing channel in the public Gopher Slack. It's a very active channel. The Gopher Slack in general is very active. It's a wonderful community. So please join them if you haven't before. And join the fuzzing channel. There's so much happening there and neat tools and updates that are happening. So join that to get started. And let's just do a quick recap. We've discussed the components of the fuzzing API. We found a bug in action during the demo. Whether it's a bug in the standard library or in my code is still up for debate. We've explored some of the internals on how the fuzzing engine works. And we've walked through several common use cases. Hopefully, you're now excited to use fuzzing for your own code. And hopefully, it should be just as easy to write as a unit test. Thank you so much. I can talk for you. They were saying that I have time for questions. I know it can be a little intimidating, but please don't be, because I have lots of things to talk about with fuzzing. It's my favorite topic, so it will only make me happy to ask questions. So please do. We just need to find a working microphone.
1, 2. 1, 2.
Oh, we got two working microphones. Perfect. Okay. I'll come out from behind the podium. I'm also happy to refresh any things I've already talked about, too.
Thank you for the presentation.
Yes,
I just had one question. You were starting from a unit test for fuzzing, and do you think it could be applied for other kinds of tests, like more long-running tests?
I'm not sure I understand your question.
No, so for example, like you were working on a test that is only testing a function.
Yeah.
But what if this test would test an API or
what you're
a
saying.
REST endpoint or something
Yeah,
like that?
yeah. Okay, so I understand your question now. So you're basically saying, can you basically put anything you want to, including long-running testing, inside of a fuzz target? The answer is kind of no. It's not really what fuzzing is for. So fuzz tests, you don't have to do it this way, but typically a fuzz target should be very fast, and it should be deterministic. So if it's something that has to make a bunch of network calls, or there's some level of randomization in it, so it can't reproduce the same thing if it runs it twice, then probably that's not a good candidate. But what you can do is find the components of that, API call through the stack, and take this helper function and fuzz that, and this helper function and fuzz that. So it's a very clear input-output. So you can't apply fuzzing everywhere. So yeah, if it's going to be a huge, long-running thing, it's probably not what fuzzing should be for. It's going to be really memory-intensive. Yeah.
Thank you.
Yeah, no problem. I also didn't mention this, but there's great tools out there that can run fuzzing continuously, like OSS Fuzz. So please check those out too. Hello.
Hello. Sorry, I'm not a Go expert, but I do have a question regarding the application to other languages.
Yeah.
So if I understand properly, and correct me if I'm wrong, but this is basically applying evolutionary algorithm to testing with inputs being evoluting with error and going into the direction of errors. So. And you showed a bit how you implement that with a function, because you can't control, as you said, you can't control the output. So if I wanted to implement that into another language, so I could do that. I could implement some kind of evolutionary algorithm to generate inputs. Yeah. And is it what the fuzzing engine is? Can you interact with it like with an evolutionary algorithm? Can you configure it with in some sort?
Yeah, so it's not configurable now. There have been discussions about having sort of like a plug-and-play configurable fuzzing engine that you can choose. So there are other fuzzing engines. There's no particular reason why our fuzzing engine for Go is better, other than the fact that it's natively written, so you don't have to download additional tools to use it. But there's tools out there like libfuzzer. If you're familiar with libfuzzer, that's a very well-known fuzzing engine for the C++ community. So a lot of people use that. There's probably fuzzing tools out there for every language in different ways, but also you don't have to use those if you don't want to. Like you said, you could just do that random, monkey approach if you want to too, or you can make it slightly more advanced. There's a lot of papers out there and research out there for kind of new advanced fuzzing features. So you could write one, but there's a good chance that there's already one out there for your language.
Okay, thank you.
More questions? I see a hand there. Hello.
Hello, thank you for the presentation. As you said, the first test go with the in complement of the unit test. So my question is, once you've run your first test to be sure your unit test have not missed any case, do you keep your first test in your code base? Do you still run them because they're...
Yeah, that's a great question. I think you should. Yeah. So like I was showing in that example, it found a bug and it found the regression test. It basically put that regression test into a file. So if you check that in, that's a free regression test. You could just copy those inputs and put them in your unit test if you want to, but it's a free regression test. It's there for you. When you run Go test, it will run those inputs too. And if you have another bug in the future that is the same, it will find that again. It's not going to run fuzzing by default because that's a lot of work. You can also use tools like I was saying before at the end there, like OSS Fuzz, which is a tool that can continuously run fuzzers. The community has actually been using this for a while, and sometimes fuzzing engines or fuzz tests run for months or like literally years until they find a bug. Sometimes it takes a really long time. Like there have been several security vulnerabilities in the Go language that were caused by some super obscure input that took months of it running to find, but it was a security vulnerability. And it's good that we found it with a fuzz test rather than someone who was malicious and trying to find it. So yeah, they have more power the longer you can run them. So having something that can run them continuously and report issues to you is the most effective way of using it, I would say. So yeah, I would keep it in your code base.
Okay,
personally.
thank you.
Yeah. I think we have one more question to your right there. Hello.
Hello, thank you for the presentation. I have one question. At some point, you mentioned that the fuzzing engine relies on coverage. Does it mean that it relies on having the source files, or is it coverage relying on the binary? Because I also know that fuzzy testing is also used, for example, to detect security vulnerabilities when you don't have the source code. So, yeah.
Yes. So what it does in this way is basically when you're running testing with the Go command finds all of the, like the compiler basically, it finds all of the files that it needs to run your code, all the packages that it needs based on the dependency graph, and then it bundles them all up, and then it uses those to run it and makes executables that way. In the fuzzing engine for Go, when you pass that -fuzz flag, it's telling the build time, it's telling the compiler at that moment to instrument your code. So actually what's happening is that your binary turns into these like little counters that pop up all over all the code that your fuzz test could feasibly hit. And so if you hit a file, like a line in a file that previously wasn't hit by fuzzing, it will report that to you, or basically add that to the interesting corpus of sorts. So as it runs, it'll actually show you, new interesting inputs that are coming. It'll say, oh, now we have 15 interesting inputs. Now we have 20 interesting inputs. And what that's doing is actually looking at the counters that are happening as it's running in real time and keeping track of them. So yeah, you do need the source code, I suppose, to run it. But yeah, that's again where it's not really great for testing, needing to make an API call to some other code base, right? It's more effective for fuzzing the code that you have.
Okay, thank you, Katia. I
Thank you
think
so much.
we ran out of time.
That's fine.
Thank you.
Thank you.